All right, by popular request, we're gonna have intro music, and then I realized this is gonna go on YouTube, so I can't have like demonetized copy strikes or whatever. So we're actually not gonna have intro music. We're just gonna have a little noodle. All right, I'll have to think about copyright things. I was gonna play "Don't Stop Believin'," and then I'm like, I don't know about that. Okay, so let's talk about math. Wait, I should have done the Beach Boys. It's Good Vibrations. I'm so dumb. I literally just thought of that, you guys. I'm not even pretending. Okay. Um, maybe we'll have Beach Boys in the future if I can get around the algorithm. Let's talk about molecules, okay? And first, this is a complete brag, but the course has been approved. This has been voted and will officially be a required MSc course in the future. So it's going to become MSc 254, Introduction to, I don't know, Mathematical and Computational Methods or something like that. So that's exciting. Great. Let's talk about molecules. Did you know that they do things? It's pretty crazy actually. And I actually make a point of saying that because when we think about molecules, at least often the cartoon in my head is I just have like sort of the ball and stick model, right? I've got two or three or four balls and they're just connected by little lines and it just sort of moves around as a unit floating through space or whatever. But that's really not accurate at all. They're extremely dynamic systems. These bonds have all kinds of different excitation modes. They have vibrational modes and bending modes and twisting modes and like it's a very, I mean, not literally a live system, but it's a very alive system in the sense of having this dynamic, irregular motion that we'd like to be able to understand in terms of basic frequencies. So that's what we're doing today is looking at that analysis of how you take something that's actually very complicated, like molecular resonance states, and expressing them in terms of basic features and fundamental frequencies that we can actually calculate. This is really important for characterization purposes because anyone who is taking or has taken 360 will have done this in lab, that we use infrared light to measure the response of materials to radiation, and based on the different bond modes that are excited by the infrared light, we can figure out which bonds are present in the material and use this to understand its chemical structure more in more detail. So, a very practical topic, something that is used a lot in the lab. And the particular technique that is used very commonly for studying organic materials in particular is Fourier transform infrared spectroscopy. We will be looking at Fourier transforms later this semester. I'm really looking forward to that. It's one of my favorite topics. That and linear algebra are really probably my top two, and they're closely related to each other. Surprise. So, spoilers. But I kind of said this already. For doing this as an experimental technique, the end application of the math to saying, okay, how do I use this in the world? This is the why it matters. Is we take infrared light with a lot of different frequency content. So we have light that spans many different wavelengths, and we illuminate our material with this light. And what you look for then is for certain frequencies of light to get absorbed. And then you take your reflected light from the material and you process it and you say, okay, which frequencies are missing? Those are the frequencies that were absorbed by my material. And where do those frequencies go? They go into exciting the molecules. They're going to provide the quanta of energy that are needed to take these bonds and promote them up to excited states, to go from their ground state of doing nothing particular up to a rotational state or a twisting state or a bending state or a vibrating state, whatever it might be. So this is very cool stuff. It's very useful, not only for organics, but especially for organics. It's a great topic. All right. Here is my definitely not stolen straight from the internet, not particularly high resolution image, but just so you can picture these things a little bit more as I get into the math, here are some common different modes. And so you can see here that we have two categories being illustrated. we're using carbon dioxide as an example. It's sort of it's the right system to start with because it's just complicated enough to let you practice the math, and it is simple enough that it doesn't completely blow your mind and explode with difficulty. So we have stretching modes on the left, and the arrows here aren't very clear, but a stretching mode would be something like this. So along the symmetry axis of the molecule, it's a linear molecule. That's also one of the reasons we start with CO2. It's easier than water because water doesn't have its 3 atoms on a straight line. So the stretching mode would be the in and out motion of the 2 oxygens on the side, but it can be symmetric or asymmetric, which is to say that you can have the 2 oxygens, moving symmetrically, so moving as mirror images of each other around the carbon, or they can move asymmetrically. You can have one oxygen that is moving further than the other one. And then a couple of the bending modes are illustrated here as well. And I know I just said something about carbon dioxide being a linear molecule. In its ground state, it is. But once you excite it, once you give it infrared light so that the bonds start doing stuff, then those oxygens can move in all kinds of different ways, and they don't have to stay in a single line with each other. So this twisting mode, for example, bending twisting, you can see that one of the oxygens starts moving at an angle while the other stays in the original line of the molecule. And then for the wagging mode, that's, again, let me just draw the arrows here. So that's going to be where the oxygens move in a direction that is perpendicular to the original line of the molecule. Is this on the test? Well, it's not on this test, but it is good stuff to know as a materials person. I heard things are made out of molecules. So let's deploy some math to solving this problem. We are going to have coupled oscillators. And the thing that couples them is, actually, before I write the equations, in a picture like, I'll take the asymmetric stretching molecule here. You can see that the length of this bond is related to the length of this bond. The molecule is staying nearly the same length, but the distance between the oxygen and the carbon, and that's kind of like how far we're stretching our spring, if you think of the springy bond kind of model. How far we stretch the spring depends on where all the atoms are in the problem. If one of the atoms move, the distances between neighboring atoms are all potentially affected by that motion. So all of our bonds can change in length dependent on the positions of all the atoms in the molecule. And that's what makes this a coupled system. So we are going to use a spring model. We have essentially F equals Kx here. And this x1 and x2, then this is the position of atom 1, and this is the position of atom 2. And we have, in this case, 2 different masses involved as well. So the big M's will be the oxygens, because oxygen is more massive than carbon, and little m will be the carbon because, well, it's littler. So we have these 3 different equations because we have 3 atoms in the system. So we have one differential equation for each atom, and the forces acting on that atom depend on its bonds and which neighbors it's bonded to and where those neighbors are. That's why we have 3 equations here. And I know you're tired of dealing with my nonsense here, but if only we had a technique for solving such a problem. If only we had a way for solving coupled systems of linear equations. That would be so great if we did. Alas, lecture over. No, of course not. I'm also looking at the slide and I realized I said something wrong earlier. This atom, the big M, this is actually the central atom. And the reason you can tell is that this central atom has 2 bonds acting on it, right? X2 is atom number 2. That's our atom in the center here. And it's got its bond with atom number 1 and its bond with atom number 3. So this actually should be the carbon in the center, and this should be the oxygen on the end, and this should be the oxygen on the other end. And apparently I don't know atomic masses. Sorry about that. All right. Yeah, we're going to solve this with matrix methods. Just like the stuff that you saw last week, this is very much, hey, here's an application of those methods to material systems. Kind of the point of this class, right? Let's use math to learn about materials. So we do a little bit of division just to clean things up. And we now have three equations, which are second derivative equals some linear combination of the individual position functions for the three atoms in the system. And this thing we can now convert to a matrix because we have the coefficients for the different terms. Those will be the elements in the coefficient matrix. So I've written it out here. Here's the matrix multiplication form. Here's our vector of second derivatives. Here's our vector of positions. And then in the middle, this is the matrix of all of the different coefficients. K is the spring constant of the bond. Again, bonds aren't actually springs, but we're modeling them like springs because it's not a bad approximation, especially near equilibrium. Very far from equilibrium, this approximation does become inaccurate, but near equilibrium, it works pretty well. All right. So we have now converted these three coupled second order differential equations to matrix multiplication. Good start. So now we need to solve for the eigenvalues and eigenvectors of this matrix. So the eigenvalues tell us the vibrational frequencies of the bonds in the system, and it depends on the stiffness of the bonds and the mass of the atoms. And you're like, okay, qualitatively, that makes sense. If I have stiffer bonds, things are going to vibrate faster. If I have more massive atoms, things are going to vibrate slower. They have more inertia. So that's reasonable. That's why we have K over M in all of these terms. We have the stiffness and the inertia working against each other in a sense. Now, when we did the simple harmonic oscillator problem, I pointed out this thing, hey, remember from physics 140 that the frequency, and specifically the angular frequency, so radians per second, is square root of K over M. So the eigenvalues of this matrix, just like all the elements in the matrix, have units of frequency squared, radians squared per second squared. So the eigenvalues will give us the special frequencies of the system. Well, the square root of the eigenvalue to be exact. So what about the eigenvectors? What's the meaning of these vectors? This is actually very cool. It took me a while to wrap my head around this the first time I saw it. It's one of those things that if you don't think about it at all, it makes sense. And if then you start to think about it, it doesn't make sense. And then if you really, really, really think about it, it makes sense. So I can't tell you how to live your life, but just be aware that that's the journey for this one. Okay, the normal modes of the molecule. This is a term that comes up fairly often when talking about vibrational stuff, not only in molecular context, but just vibrations more generally. The eigenvectors are going to tell us the normal modes of our molecule. What's a normal mode? A normal mode is a particular pattern of movement of the atoms. It's like that figure, the definitely not stolen figure that I had a few slides ago that showed the atoms moving in different ways, in plane or out of plane, on angles, right angles, straight lines. Those are the different normal modes of the system. And what's cool is that when we actually solve for the eigenvectors, we're going to get numbers based on the stiffness of the bond, based on the mass of the atoms. We get actual numbers for these things. And those numbers tell us about the motion of the individual atoms in the vibration of the molecule. So like in this example I have here, if we got an eigenvector -1, 0, and 1, that is the symmetric stretching mode because the atom on the left is going to move left while the atom on the right moves to the right. That's the negative and the positive here. Meanwhile, the center atom just sits still because it is the center of mass that the other atoms are vibrating symmetrically around. So this gives us actually like a very tangible physical meaning of the components of the eigenvector. They tell us about the displacements of the individual molecules, or sorry, individual atoms in the molecule. So for the set of eigenvectors that you find, that is going to give us the set of different vibrational modes for the molecule. And then the bookkeeping step, as always, you want to keep track of which eigenvector and which eigenvalue go together, because then that tells you the frequency of that particular normal mode of the molecule. It's good stuff. Now I have to use my linear algebra language a little bit. The eigenvectors do form a complete basis for the space that we're in. That has not changed from before. What that means in terms of physical things for the actual molecule itself is it says that any vibration of the molecule can be expressed as a linear combination of the normal modes. Yes, I just read the slide out loud. I do that rarely, so you know when I do, it's a big deal. Any vibrational action that this molecule experiences can be written as a sum of this amount of vibration number 1 plus this amount of vibration number 2 plus this amount of vibration number 3, however many there are. And that lets you then take potentially very complicated motions, very complicated excitations of the molecule, and break it down into simpler parts that you can analyze individually, which is great. We love taking complicated things and making them simpler when trying to solve them. Then the linear combination that you build, so if you're like, okay, here's my vibration of the molecule, it's going to be twice the first eigenvector plus 3 times the second eigenvector minus 1 times the third eigenvector. So something like this. I just made up an example here. But these coefficients, that is how much of that mode is present in the total vibration. So it really is a linear combination in the most direct sense. It's saying I have some amount each of a few different things, and then I smush them all together. And they happen simultaneously and add up to a total compound motion or action or vibration of my system. And the reason I point out this business about the coefficients is another connection to Fourier transforms, which when we get to that toward the end of this semester, this idea of how much of each frequency is present, what is the strength of the different frequency components in the system, that is a critical concept in Fourier analysis. So I like the fact that we get a little teaser of it here when we can talk about the vibration of one molecule and ask how much of each different component normal mode of the molecule is present in a more complicated activity. All right, that's it. This is the only video for today. There is not a second one, so don't go looking for it. You can get ahead if you want to. I won't stop you, of course. I also want to point out that this is the bare bones introduction to the topic. There are more complications needed when you start to look at bigger systems of interacting parts that vibrate with each other. So if we wanted to look at a crystal structure like a lattice and to ask what are the vibrational modes of this lattice, you absolutely can apply this framework to a more complicated problem like that, but you do need some other tools in the math toolkit that I'm just not going to get to this semester. So there will be a couple questions about molecules on the homework, but you won't be directly applying this differential equations like solution technique to these problems. I just want you to have the concepts in mind because I think this is a neat topic. It's a fun way to see all of this eigen stuff applied to something that's a little bit more tangible. So yeah, I hope you liked it. And the other thing I'll just point out real quick is there is an extra problem on this week's homework compared to normal. So I did want to cut down the lecture time a little bit today to, try to make things balance out. So that's it. Thanks for playing along, and I will see you next time.